What if I told you that the universe has a secret language, one that isn't written in equations or codes, but in shapes? For thousands of years, some of the greatest minds in history have looked up at the night sky and sensed a hidden order, a kind of cosmic architecture built not from matter alone, but from geometry. Think about that for a moment. The same geometric principles that define a snowflake or a honeycomb might also govern the spin of a galaxy or the birth of a star. It's a breathtaking idea that from the infinitely small to the impossibly vast, everything is connected through patterns, angles, and symmetries. This isn't just poetic speculation. Centuries ago, Plato proposed that the entire cosmos could be understood through 5 perfect shapes, the Platonic solids, which he believed were the fundamental building blocks of reality. Later, Johannes Kepler became so captivated by this notion that he dedicated years of his life to fitting those same shapes between the orbits of the planets, convinced that geometry held the key to celestial harmony. They were onto something profound. Today, with tools like the Hubble and James Webb telescopes, we're seeing farther and deeper than ever before. And what we're discovering is that the universe really does seem to be written in the language of geometry. In this video, we're going to explore that extraordinary idea together. We'll travel from the timeless elegance of Plato's forms to the mind-bending structure of the cosmic web, a vast architecture of galaxies, clusters, and voids that mirrors geometric patterns on a scale almost too grand to comprehend. We'll see how geometry shapes black holes, guides the expansion of the universe, and even helps explain why the world around us looks and behaves the way it does. This is more than a story about math or science. It's about seeing the universe with new eyes, recognizing the hidden connections that tie everything together, and rediscovering a sense of wonder that has inspired dreamers and discoverers for millennia. So come with me, let's unravel the geometric blueprint of the cosmos and see just how deep the patterns go. Long before telescopes or particle accelerators, one of history's greatest thinkers peered into the nature of reality and saw geometry. In his dialogue, Timaeus, the Greek philosopher Plato made a breathtaking proposal that the entire physical world, in all its complexity, could be reduced to just a handful of perfect geometric forms. He assigned the 4 classical elements to what we now call the Platonic solids. To earth, he gave the stable, unmoving cube. To air, the graceful octahedron. To fire, the sharp, penetrating tetrahedron. And to water, the flowing, multifaceted icosahedron. But there was a 5th shape, the dodecahedron, which Plato reserved for the heavens themselves, suggesting it was used by the gods to arrange the constellations. This wasn't just a poetic metaphor. Plato sincerely believed these shapes were the literal building blocks of the cosmos, the fundamental particles of his time. What's truly remarkable is that Plato arrived at this idea not through experiment, but through pure reason and philosophy. He was operating on a profound conviction that the universe must be built on order, not chaos, that beneath the messy surface of reality lay a perfect, rational, and mathematical blueprint. He saw these 5 solids as the only possible forms that could satisfy this cosmic perfection, each one constructed from identical regular polygons with the same number of faces meeting at every vertex. In a world without modern science, this was a staggering leap of intuition. It was the first major attempt to describe the physical universe not through mythology, but through mathematics and geometry. This vision of a geometric cosmos didn't just fade into history. It became a cornerstone of scientific thought for over 2,000 years. Plato's Academy in Athens famously bore the inscription, "Let no one ignorant of geometry enter here," cementing the central role he believed math played in understanding the world. His ideas influenced astronomers, architects, and artists through the Renaissance and beyond, creating a lasting legacy that sought to find harmony and proportion in nature. Even when later science moved beyond the four elements, the core idea that the universe has a geometric foundation proved incredibly resilient. It's as if Plato caught a glimpse of a deeper truth, a hint that the language of nature is indeed written in shapes and symmetries, waiting for us to learn how to read it. Centuries after Plato, another brilliant mind became utterly captivated by the idea of a geometric cosmos. Johannes Kepler, a German mathematician and astronomer living in the late 16th and early 17th centuries, was a man driven by a profound, almost spiritual conviction that the universe was structured according to a divine geometric plan. He was deeply inspired by Plato's work, and he set out on an ambitious quest to find the geometric harmony hidden within our solar system. Kepler was convinced that the distances between the planets and their orbits around the Sun weren't random. They had to follow a pattern, a cosmic music based on perfect mathematical forms. His grand idea was both beautiful and, to our modern eyes, strikingly unconventional. He proposed that the six known planets Mercury, Venus, Earth, Mars, Jupiter, and Saturn orbited within a set of nested spheres. The spaces between these spheres, he believed, were precisely defined by the five Platonic solids. Imagine a Russian doll, but instead of dolls, it's a series of perfect shapes. At the center was the Sun. Wrapped around it was the orbit of Mercury. The space between Mercury and Venus was filled by an octahedron. Encasing that was Venus's orbit, and the gap between Venus and Earth was filled by an icosahedron. This intricate nesting continued outward. A dodecahedron between Earth and Mars, a tetrahedron between Mars and Jupiter, and finally a cube between Jupiter and Saturn. In Kepler's mind, this elegant model explained why there were only 6 planets, because there were only 5 gaps between the spheres to be filled by the 5 perfect solids. He dedicated years of his life to this model, refining calculations and measurements, utterly devoted to proving this celestial harmony was real. He published his findings in 1596 in a work called Mysterium Cosmographicum, the Cosmic Mystery. While the specific model of nested solids was ultimately incorrect, Kepler's relentless pursuit of it led him to something far more lasting. His insistence on precise geometry forced him to acquire the incredibly accurate astronomical data collected by his mentor, Tycho Brahe. And it was this painstakingly detailed data that eventually showed him his beautiful model didn't quite fit. The planets simply refused to obey the perfect nested spheres. But rather than abandon his core belief in a geometric universe, Kepler pivoted. He realized the geometry wasn't in the spaces between the orbits, but in the motion of the orbits themselves. This led him to his 3 revolutionary laws of planetary motion. He discovered that planets move in ellipses, not perfect circles, with the Sun at one focus, a monumental break from 2,000 years of astronomical tradition. He found that a planet sweeps out equal areas in equal times, meaning it moves faster when closer to the Sun. And he formulated a precise mathematical relationship between a planet's orbital period and its distance from the Sun. These laws didn't just describe how planets move. They revealed that their motion was governed by mathematical rules. This was the true, lasting triumph of Kepler's geometric approach. He had started with Plato's perfect forms, but he ended up discovering the actual geometric laws that operate in the real, imperfect heavens. His work provided the crucial celestial blueprint that Isaac Newton would later use to formulate his law of universal gravitation. Newton famously stood on the shoulders of giants, and Kepler was one of the tallest. Without Kepler's geometric laws describing how the planets moved, Newton might never have deduced why they moved, the invisible force of gravity acting at a distance. And this geometric thread didn't stop with Newton. Centuries later, Albert Einstein's theory of general relativity would describe gravity itself not as a force, but as the geometry of spacetime curved by mass and energy. Kepler's dream of a geometric cosmos, born from Plato's perfect solids, ultimately found its most profound expression in Einstein's equations. Kepler's journey is a powerful reminder that the path to scientific truth is rarely a straight line. It often wins through beautiful, flawed ideas, but the pursuit of elegance and order can itself be the guiding star that leads to monumental discovery. He married the wild imagination of a mystic with the rigorous observation of a scientist, and in doing so, he gave us the first true glimpse of a universe written in the language of geometry. So what exactly are these 5 perfect shapes that so captivated Plato and Kepler? Let's meet them properly. First is the tetrahedron, a pyramid built from 4 equilateral triangles. It's the simplest, sharpest, and most stable of the group. Next, the cube or hexahedron with its 6 square faces, a symbol of solidity and earth. Then the octahedron, essentially 2 pyramids base to base, made of 8 triangles, often associated with air for its graceful, floating quality. The icosahedron is next, a complex and beautiful structure with 20 triangular faces representing the fluidity of water. And finally, the dodecahedron, the most mysterious of the set, with its 12 pentagonal faces, which Plato reserved for the constellations, the shape of the heavens themselves. What makes these 5 shapes so special, and why are there only 5? It all comes down to a simple but profound rule of geometry. For a shape to be a Platonic solid, every single face must be an identical regular polygon, all squares, all pentagons, all triangles, and the exact same number of these faces must meet at every single vertex or corner. It seems like a simple requirement, but it creates an incredibly strict set of conditions. Think about trying to build one. You can't just slap polygons together any way you want. The angles have to add up perfectly around a point in 3-dimensional space without any gaps or overlaps. It's like a cosmic puzzle with only 5 possible solutions. For example, you can fit 3 equilateral triangles around a point. That gives you the tetrahedron. Fit 4 and you get the octahedron. Fit 5 and you create the icosahedron. But try to fit 6 equilateral triangles around a single point, and the angles add up to 360 degrees. They lie flat on a plane. You can't bend them into a 3rd dimension to form a closed solid. The math simply forbids it. The same strict logic applies to the other shapes. 3 squares make a corner of a cube, but you can't have 4 squares meeting at a point in 3D space for the same reason. They'd lie flat. And with pentagons, 3 around a point create the corner of a dodecahedron, but that's the only possible configuration. You can't use hexagons or any polygon with more sides, because their angles are too large to fit 3 or more around a point without exceeding the necessary space. This elegant mathematical constraint is why, in our 3-dimensional universe, there are only 5 of these perfectly symmetrical forms. They are the exclusive members of a very elite geometric club. This perfect symmetry is what has made them objects of fascination for millennia, far beyond the realm of philosophy. Artists like Leonardo da Vinci and Albrecht Dürer were mesmerized by their proportions and incorporated them into their work. Architects have used them to design everything from ancient temples to modern geodesic domes. For mathematicians, they are a gateway into deeper fields like group theory and topology, providing a perfect, tangible example of abstract symmetry principles. Their balance and harmony feel inherently beautiful to us, appealing to a deep-seated human love of order and pattern. But perhaps the most compelling evidence for their significance is that they aren't just human inventions. They appear again and again in the natural world. The tetrahedron shows up in the bonds of a carbon atom at the heart of a diamond. The cubic structure is the preferred arrangement for crystals of table salt. Many viruses, like the adenovirus, have icosahedral shells because it is the most efficient way to enclose a space with identical protein subunits, a marvel of geometric efficiency at the nanoscale. Even in the seemingly random formation of bubbles in foam, The geometry tends toward these stable, low-energy configurations. It's as if nature, when left to its own devices, arrives at the same perfect solutions that the ancient Greeks discovered through pure thought. This uncanny presence in both the abstract world of mathematics and the physical world of atoms and organisms suggests something profound. The Platonic solids are more than just interesting shapes. They seem to be fundamental templates, a limited set of blueprints that reality can choose from when building stable, symmetric structures. They hint at a deep, underlying order to the universe, a geometric substrate that governs form and function from the smallest scales to the largest. They are a beautiful reminder that chaos is often just a surface feature, and beneath it lies a world of exquisite mathematical perfection. This drive toward geometric order isn't just a philosophical idea or a celestial blueprint. It's happening right now, all around us, on a scale so small we can't see it. Take an ordinary grain of table salt. To our eyes, it's just a tiny white cube. But if you could shrink down to the size of an atom and peer inside, you would witness a breathtakingly precise geometric dance. Sodium and chlorine atoms alternate in a perfect, three-dimensional grid, forming a pattern of exquisite symmetry. This is the cubic crystal system, and it's a direct, real-world echo of Plato's cube, the shape he assigned to the element of Earth for its stability and solidity. It turns out he was more right than he could have ever known. This phenomenon isn't unique to salt. In fact, it's a fundamental rule of the material world. Atoms and molecules, when given the chance, almost always arrange themselves into highly ordered, symmetric patterns called crystal lattices. They do this for a beautifully simple reason: efficiency. Nature, at its core, is a relentless optimizer. A symmetric, repeating pattern is the most efficient way to pack atoms together, minimizing the energy between them and creating the most stable, low-energy state possible. It's the physical equivalent of packing oranges in a crate. The tightest, most stable arrangement isn't random, it's a repeating, geometric pattern. This universal tendency toward geometric order is why a diamond, made of carbon atoms linked in an incredibly strong tetrahedral network, is the hardest natural substance on Earth. And it's also why a snowflake, as it forms, expresses the same six-fold symmetry in a million unique, intricate ways. The geometry of the water molecule itself dictates the angles at which new molecules can bond, building a fragile crystal that is never repeated yet always obeys the same geometric rules. To make sense of this incredible diversity of crystalline forms, scientists use a branch of mathematics called group theory, which is essentially the formal language of symmetry. Crystallographers don't just look at a crystal and say, "That's a cube." They use group theory to classify every possible way atoms can be arranged in a repeating pattern that fills space. This classification system has revealed that there are precisely 230 possible distinct symmetries for crystals in 3 dimensions. These are known as space groups, and they are the complete catalog of all the geometric blueprints that matter can use to build a solid. Think about that for a moment. Every crystal structure ever found in every mineral, every metal, every gemstone, every fleck of frost on your window conforms to one of these 230 geometric patterns. It's a stunning limitation and a profound revelation. The chaotic, vibrant diversity of the solid world emerges from a surprisingly small and elegant set of geometric rules. This discovery connects the microscopic world directly to the grand cosmic scales we've been exploring. The same geometric principles that dictate how carbon atoms bond in a diamond also govern how galaxies cluster in the vastness of space. The drive towards symmetry and low-energy states is a universal theme, a thread that runs through the fabric of reality at every scale. The cubic lattice of a salt crystal is a tiny, perfect echo of the larger geometric order that shapes planets, stars, and the cosmos itself. It is a powerful testament to the fact that geometry isn't just a human invention for describing the world. It is literally woven into the structure of the world, an active force that guides how matter assembles itself, from the ground beneath our feet to the distant edges of the observable universe. But if crystals show us geometry's role in organizing matter, then fundamental physics reveals something even more profound. That symmetry isn't just a property of the universe. It is, in a very real sense, the universe's chief architect. At the heart of every particle, every force, and every interaction lies an abstract, almost ethereal geometric principle that dictates what is possible and what is not. This is the world of gauge symmetry and Lie groups, concepts that might sound impossibly complex, but are actually the hidden gears turning behind the scenes of reality itself. Think of it this way. Imagine a perfectly smooth, featureless sphere. You can rotate it any way you want, and it looks exactly the same. That's a very simple, obvious kind of symmetry. Now, imagine that sphere represents a fundamental field that fills all of space, like the electron field. The laws of physics, it turns out, possess a similar kind of symmetry, but it's a local symmetry, meaning the rules of the game don't change even if you make a different rotation or adjustment at every single point in space and time. This requirement, this unshakable geometric demand that the laws of physics must look the same no matter how you tweak these abstract fields locally, isn't just a mathematical curiosity. It actually forces new particles and new forces to exist to maintain that perfect symmetry. It's as if the universe is so insistent on geometric harmony that it will invent entirely new phenomena just to preserve it. This is the breathtaking power of gauge symmetry, and it's the very engine that drives the standard model of particle physics. The symmetries encoded in mathematical structures known as Lie groups are the reason we have the electromagnetic force, the weak nuclear force, and the strong nuclear force. For example, the symmetry group known as U1 gives us electromagnetism. The photon, the particle of light, emerges not as a primary entity but as a necessary consequence, a force carrier required to keep the equations symmetric when we change how we describe the electron field. It's a geometric correction, a cosmic balancing act. Similarly, the symmetry groups SU2 and SU3 give us the weak and strong forces, complete with their own force-carrying particles, the W and Z bosons for the weak force, and the gluons for the strong force that holds atomic nuclei together. The quarks and leptons that make up all matter are themselves representations of these deeper symmetries. Their properties, their charge, their mass, their very existence, are dictated by how they fit into this grand geometric scheme. This geometric framework is so potent that it allows physicists to predict the existence of particles before they are ever seen. The Higgs boson, discovered at the Large Hadron Collider in 2012, was predicted decades earlier because the mathematical structure of the Standard Model, its specific symmetries, had a hole in it, a missing piece required for the entire geometric edifice to remain consistent and for particles to have mass. Its discovery was a monumental triumph not for a specific theory of matter, but for the power of symmetry itself as a guiding principle. And the quest for geometric unity pushes even further. Supersymmetry is a proposed extension of these ideas, a new symmetry that would connect the two fundamental classes of particles, fermions, the building blocks of matter, and bosons, the carriers of force. It suggests that for every known particle, there is a hidden, superpartner particle. This isn't just about adding more particles to a list. It's about revealing a deeper, more beautiful geometric symmetry at the heart of reality, one that could seamlessly weave together all forces and matter. While evidence for supersymmetry remains elusive, its pursuit highlights a central truth in modern physics. The search for a unified theory is, at its core, a search for the ultimate, most profound symmetry. These abstract geometric principles are not just tools in a physicist's toolkit. They are the fundamental language in which the laws of the universe are written, connecting the behavior of the smallest quanta to the grand dynamics of the cosmos. But if the symmetries of particle physics revealed a hidden geometric order governing the quantum world, it was a different kind of geometric revolution that would forever change our view of the cosmos on the grandest scale. For centuries, since the time of Newton, gravity was understood as a mysterious, invisible force, an instantaneous pull between objects across empty space. It was a useful idea, but it left a fundamental question unanswered. How does this force actually work? What is the mechanism? Albert Einstein spent a decade grappling with this puzzle, and his answer was so radical it rewrote the rules of the universe. He proposed that gravity isn't a force at all. There is no pull. Instead, what we perceive as gravity is simply the geometry of spacetime itself. Imagine the universe not as a static stage where events play out, but as a vast, flexible fabric. A four-dimensional tapestry woven together from the three dimensions of space and the one dimension of time. Now, place a massive object like our Sun onto this fabric. Its immense mass causes the fabric to warp and dimple, creating a curvature in the very structure of reality. Now, take a smaller object like our Earth. It isn't being pulled by an invisible string from the Sun. It's simply following the most natural, straightest possible path through this curved geometric landscape. The planet's orbit isn't a forced ellipse, it's a geodesic, the equivalent of a straight line on the curved surface of a sphere. The Moon orbiting the Earth, a satellite falling around our planet, an apple dropping from a tree. They are all just following the contours of warped spacetime. The force is an illusion, the geometry is everything. To express this breathtaking idea mathematically, Einstein needed a new language, a new kind of geometry that could describe curved, dynamic surfaces. He found it in the work of a 19th-century German mathematician named Bernhard Riemann. Euclidean geometry, the geometry we learn in school, is perfect for flat planes and simple shape. It's the geometry of a sheet of paper. But the universe is not a flat sheet of paper. Riemannian geometry provided the tools to describe spaces that could be curved, twisted, and stretched in any number of dimensions. At the heart of this description is the metric tensor, a mathematical object that acts like a detailed topographic map for spacetime, specifying the distance between any 2 points and how that distance is distorted by the presence of mass and energy. Einstein's field equations are the master key that unlocks this map. They are a set of incredibly complex, interwoven equations that essentially say one profound thing. The curvature of spacetime on the left side of the equation is directly proportional to the energy and momentum of matter and radiation on the right side. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. It's a perfect, closed, geometric dance. This single insight didn't just refine Newton's law. It completely reinvented our concept of reality, predicting phenomena that were previously unimaginable. It predicted that if spacetime could be curved, then light itself, which always travels the straightest path, must bend as it passes near a massive object. This was confirmed during a solar eclipse in 1919, when stars near the Sun appeared to shift from their known positions, their light warped by the Sun's gravitational field. It predicted that the powerful gravitational field of a dense, massive object could slow down time itself, a phenomenon known as gravitational time dilation, which we now account for in the ultra-precise clocks of GPS satellites. Most spectacularly, it predicted that cataclysmic cosmic events, like the collision of two black holes, could send ripples through the very fabric of spacetime, ripples we now call gravitational waves, which were directly detected a century later by the LIGO Observatory. Einstein's geometric vision of gravity gave us black holes, the expanding universe, and the Big Bang. It revealed that the cosmos is not a collection of objects in a void, but a dynamic, evolving geometric entity. The stage itself is alive, bending, stretching, and vibrating. Geometry is no longer just the static backdrop of the universe. It is the protagonist, the dynamic and malleable substance from which everything is made. If Einstein's theory painted a picture of spacetime as a dynamic, flexible fabric, then black holes are the places where that fabric is stretched and warped beyond all recognition, pushing geometry to its absolute breaking point. These cosmic phenomena are the ultimate expression of general relativity, regions where the gravitational pull is so unimaginably strong that nothing, not even light, can escape. And at their core, they present us with a profound geometric paradox. On one hand, the event horizon, the point of no return, is a model of geometric perfection. For a simple, non-rotating black hole, the event horizon forms a perfect, smooth sphere. Its size is defined by a beautifully simple formula known as the Schwarzschild radius, which depends only on the black hole's mass. It is a boundary of stunning geometric simplicity, a stark, silent surface hiding the chaos within. But cross that boundary, and you enter a realm where our understanding of geometry completely falls apart. At the very center of a black hole lies the singularity, a point where the curvature of spacetime is predicted to become infinite. Density becomes infinite, all known laws of physics cease to function, and the very concepts of space and time lose all meaning. It is a place where the geometric rules that govern the rest of the universe simply break down, a screaming error in the equations that tells us our current theories are incomplete. This is the great challenge black holes present. They are defined by geometry, yet they contain a point where geometry itself dies. The story becomes even more fascinating when black holes spin. In nature, almost every celestial object rotates, and black holes are no exception. A rotating black hole, described by the Kerr metric, a solution to Einstein's equations discovered by physicist Roy Kerr, is a far more complex and intriguing geometric beast. Its spin drags the very fabric of spacetime around with it, a phenomenon called frame dragging, creating a region just outside the event horizon known as the ergosphere. Within this warped zone, nothing can stand still. Spacetime itself is being pulled along like a powerful cosmic whirlpool. The geometry of a Kerr black hole is not a simple sphere but an oblate spheroid, and it possesses not one, but two boundaries, the outer event horizon and an inner horizon, each with its own strange geometric properties. The inner horizon, in particular, is theorized to be a place of infinite blue shift, where any radiation falling into the black hole could be amplified to infinite energy, another point where our geometric descriptions predict their own downfall. These extreme geometric properties make black holes the ultimate testing grounds for new physics, forcing us to look beyond Einstein's theory to reconcile gravity with the quantum world. Theories like loop quantum gravity attempt to do just that by proposing that spacetime is not smooth and continuous, but is instead woven from tiny, discrete loops, a kind of quantum fabric. In this view, the terrifying singularity at a black hole's heart might be replaced by a less violent transition, a quantum bounce into another region of spacetime. Similarly, the holographic principle, inspired by the geometric properties of black hole event horizons, suggests that all the information describing what fell into a black hole is somehow encoded on its two-dimensional surface, implying that our three-dimensional reality might be a projection from a lower dimensional boundary. Black holes, these darkest and most geometric of objects, are constantly illuminating new paths forward, compelling us to invent new geometric languages to describe the fundamental nature of reality. Yet if black holes represent a place where geometry becomes extreme, we must rewind the cosmic clock even further to a time when geometry performed its most monumental task, shaping the entire infant universe in a breathtakingly brief instant. This is the era of cosmic inflation, a theory proposing that a fraction of a second after the Big Bang, the universe underwent an exponential growth spurt, expanding faster than the speed of light itself. This wasn't an expansion into space, but a violent stretching of space-time, a geometric unfolding so rapid it smoothed the cosmos into the remarkably uniform and flat universe we observe today. The driving engine behind this incredible event wasn't some mysterious force, but a specific kind of energy field, a scalar field whose geometric properties dictated the fate of everything. To understand how this works, imagine a very different kind of landscape, not one of warped spacetime but an abstract mathematical hill. This is the inflationary potential energy landscape. At the very top of this hill sits a scalar field known as the inflaton field, trapped in a high-energy state. This state has a peculiar geometric property. It exerts a powerful negative pressure, and it's this pressure that acts as the engine for repulsive gravity, causing spacetime to expand at an accelerating exponential rate. As the universe expands, the field very slowly rolls down this potential hill. While it's up there, the expansion is furious, stretching any initial irregularities or wrinkles in spacetime to near perfect smoothness. This elegant geometric mechanism solves two of the biggest puzzles in cosmology in one fell swoop. The first is the horizon problem. Look at the cosmic microwave background radiation in opposite sides of the sky. These regions are so far apart that light hasn't had time to travel between them since the beginning of the universe. Yet, they are almost exactly the same temperature. How can two regions that were never in contact be so perfectly synchronized? Inflation provides the geometric answer. Before the rapid expansion, these regions were actually incredibly close together, in causal contact, and had plenty of time to even out their temperature. Inflation then blew them apart to opposite ends of the observable universe, preserving that uniformity across vast distances. The second puzzle is the flatness problem. Our universe appears to be incredibly flat on large scales, meaning the geometry of spacetime follows the rules of Euclid, where parallel lines never meet. The density of matter and energy is exquisitely fine-tuned to this critical value. Any slight deviation from this perfect flatness in the early universe would have been magnified over time, leading to a cosmos that either quickly recollapsed or expanded into a barren void. Inflation's geometric stretching forced the universe toward this flatness, much like how blowing up a balloon makes any small section of its surface appear flatter and flatter. The exponential expansion diluted any initial curvature, driving the overall geometry toward that critical, flat state. This entire process is governed by the geometry of the inflaton field itself and how it couples to gravity through Einstein's equations. The specific shape of that potential energy hill, its steepness, its curvature determines the duration and intensity of the inflationary period. When the field eventually reaches the bottom of the hill, it oscillates and decays, converting that huge store of potential energy into the hot, dense soup of particles that would eventually form all the matter and radiation in the universe. In this way, the geometric dynamics of a single field didn't just smooth and flatten the cosmos. It literally filled it with the raw material for everything we see today. The geometric conditions during that infinitesimally small window of time set the stage for the formation of galaxies, stars, planets, and ultimately, us. Yet if the inflationary epoch set the initial geometric conditions, the universe that followed was anything but a featureless void. For billions of years, gravity has been the master sculptor, working with the invisible clay of dark matter to carve the cosmos into its present-day form. And the result is not a random scattering of galaxies, but something far more structured and breathtaking, a vast, interconnected architecture known as the cosmic web. This is the largest pattern in existence, a sprawling tapestry of dense galaxy clusters, long, delicate filaments, and immense, empty voids that stretches across the entire observable universe. It is a structure of such grandeur and geometric complexity that it defies simple description, revealing a universe that is fundamentally ordered, even in its apparent chaos. This grand design didn't emerge by accident. It is the direct and inevitable consequence of gravity acting on the tiny, quantum fluctuations that were amplified during inflation. Think of the early universe as a nearly smooth soup of dark matter and gas, but with incredibly faint ripples regions that were ever so slightly denser than others. Over cosmic time, gravity began to work on these ripples. The slightly denser patches had a stronger gravitational pull, drawing in more and more matter from their surroundings. This process created a fascinating geometric tug-of-war. As matter collapsed inward under its own weight, it wanted to form spherical halos, the most efficient, symmetric configuration. But because this collapse was happening simultaneously from every direction across an expanding universe, the matter couldn't simply fall into neat spheres. Instead, it flowed along the paths of least resistance, creating flattened sheets and elongated filaments where those flows converged. The regions where multiple filaments met became the dense nodes of galaxy clusters. And the areas that were initially less dense were left behind, emptying out over billions of years to become the vast, dark cosmic voids. The geometry of this gravitational collapse, governed by the laws of physics, is what gave the cosmic web its distinctive sponge-like or web-like topology. To truly understand this structure, scientists don't just use telescopes. They turn to the abstract world of mathematics, specifically topology and network theory. Topology is the branch of mathematics concerned with properties that remain unchanged even when an object is stretched or bent. It's the study of connectivity. When cosmologists apply topology to the cosmic web, they aren't as interested in the exact positions of galaxies as they are in the overall shape of the structure. Is the universe more like a series of isolated clusters or a network of connected tunnels? By analyzing the number of holes, handles, and isolated regions in the large-scale distribution of matter, topology gives them a powerful tool to quantify the cosmic foam. Network theory, on the other hand, treats galaxies and clusters as nodes in an immense cosmic network. The filaments are the links between them. By studying this network, how connected it is, how many pathways exist between nodes, where the central hubs are, scientists can understand the underlying rules that govern the web's formation and evolution. These geometric and mathematical tools reveal that the cosmic web is not a haphazard arrangement. It is a highly organized, complex system with its own distinct architecture. The most compelling evidence that we understand this geometric process comes from our ability to recreate it inside a computer. The most famous of these efforts is the Millennium Run simulation. This monumental computational project started with a virtual volume of space representing a cube about 2 billion light-years on a side. It populated this space with particles representing dark matter, using the observed fluctuations in the cosmic microwave background as its initial conditions. Then, it let the laws of physics, primarily gravity, play out over simulated billions of years. The algorithms at the heart of this simulation are deeply geometric, calculating the gravitational forces between countless particles and tracking how they move and cluster together. When the simulation was complete, the result was staggering. The computer had generated its own cosmic web, an intricate network of clusters, filaments, and voids that looked almost identical to the maps being created by galaxy surveys like the Sloan Digital Sky Survey. The virtual universe had grown up to look just like our own. This remarkable agreement between simulation and observation is one of the strongest confirmations of our entire cosmological model. It shows that given the initial conditions from inflation and the known force of gravity, the geometric emergence of the cosmic web is not just a theory, but a predictable and unavoidable outcome. This vast, beautiful tapestry is the signature of a universe built on geometric principles, woven together by the relentless and predictable force of gravity. But the geometric story of the cosmos isn't just one of perfect spheres and smooth curves. For every pristine crystal or ideal black hole horizon, there is a breathtaking complexity in nature that seems to defy simple description. The ragged edge of a coastline, the lightning bolt branching of a tree, the intricate plumbing of our lungs. These forms are irregular, rough, and infinitely detailed. For centuries, they were dismissed as mathematical monsters, too messy for classical geometry to handle. That is, until a visionary mathematician named Benoit Mandelbrot asked a deceptively simple question: how long is the coast of Britain? The answer, he realized, depends entirely on the length of your ruler. Measure with a satellite and you get one length. Walk it with a yardstick, and the length increases as you follow more inlets and peninsulas. Use a tiny centimeter stick, and the length becomes even longer, tracing every pebble and grain of sand. This wasn't a problem of measurement, it was a revelation. These shapes have a property called self-similarity, meaning they look roughly the same at different scales. Zoom in on a section of coastline and it resembles the whole. Examine a tiny twig, and its branching pattern mirrors that of the entire tree. Mandelbrot gave these infinitely complex shapes a name: fractals. He didn't just name them, he gave us a new geometric language to describe them. Fractal geometry is the mathematics of roughness, of structured chaos. It provides tools like the fractal dimension to quantify this complexity. A smooth line has a dimension of 1. A perfectly flat plane has a dimension of 2. But a fractal curve, like a coastline that twists and turns so much it begins to fill space, has a fractional dimension somewhere between 1 and 2. A value like 1.26 isn't just a number. It's a measure of the shape's intricacy, its ability to pack an immense length into a finite area. This was a monumental shift in thinking. For the first time, the irregular patterns that dominate our natural world — clouds, mountains, river networks, blood vessels — could be described, measured, and compared with precise mathematics. They were no longer formless chaos. They were a different kind of order, an order built from recursion and iteration. A fractal is often generated by a surprisingly simple rule that is repeated over and over again, and feedback loop that creates breathtaking complexity from utter simplicity. And this doesn't just apply to the world we can see from our window. This same fractal order appears to be woven into the very fabric of the cosmos on the largest scales imaginable. Look at a detailed map of the universe, like the one from the Sloan Digital Sky Survey. You see the cosmic web of galaxies, a vast network of clusters and filaments surrounding immense voids. Now zoom in on one single filament. Within it, you'll find smaller clusters of galaxies. Zoom in further on one of those clusters, and you'll see it's itself made of galaxies grouped together in a self-similar pattern. The distribution of matter in the universe isn't smooth, and it isn't random. It displays a kind of statistical self-similarity. The way galaxies cluster together over a range of 100 million light-years looks remarkably similar to the way they cluster over a range of 1 billion light-years. The universe, in its large-scale structure, appears to be fractal-like up to a certain point. Cosmologists use this insight to model the formation of this structure, showing how gravity can act on dark matter in a way that naturally builds up this hierarchical, self-similar clustering from the tiny initial seeds planted by inflation. The influence of fractal thinking even reaches into the most speculative realms of theoretical physics, including the quest for quantum gravity. Some approaches propose that spacetime itself might have a fractal structure at the tiniest possible scales, near the Planck length. This idea suggests that if you could zoom in on the fabric of reality with a microscope of infinite power, you wouldn't find smooth, continuous geometry, but a wildly fluctuating, frothy, and potentially fractal landscape. This could be a way to resolve the singularities that plague our current theories, like the one at the heart of a black hole. In this view, the infinite curvature is smoothed out by the fundamental graininess of a fractal spacetime. While this remains a highly theoretical area, it demonstrates how fractal geometry has become more than just a tool for describing natural patterns. It is a new lens through which we might fundamentally reinterpret the nature of reality itself. Fractals teach us a profound lesson about the universe's aesthetic. Beauty and order are not only found in the perfect symmetry of a Platonic solid or the smooth curve of a planetary orbit. They are equally present in the chaotic splash of a wave, the jagged outline of a mountain, and the sprawling, branching cosmic web. The universe is a master of both kinds of design, the perfectly symmetric and the infinitely complex. Yet for all its grandeur, the cosmic web is a structure that emerged over billions of years. To find the universe's true geometric blueprint, we must look back to its very beginning, to a time before stars or galaxies even existed. We must look at the oldest light in the cosmos, the cosmic microwave background, or CMB. This faint, cold glow is the afterglow of the Big Bang itself, a relic from when the universe was just 380,000 years old, a mere infant. At that moment, the expanding cosmos had cooled enough for electrons and protons to combine into neutral atoms, an event called recombination. This suddenly made the universe transparent, allowing light to travel freely for the first time. That first flash of light has been stretching and cooling with the expansion of the universe ever since, and we now detect it as a uniform microwave signal coming from every direction in the sky. A lukewarm whisper just 2.7 degrees above absolute zero. But this background is not perfectly uniform. If you could see it with eyes sensitive to tiny temperature differences, you would witness a breathtakingly detailed map of the infant cosmos, speckled with minuscule hot and cold spots and anisotropies that are only about 1 part in 100,000. These tiny fluctuations are not random noise. They are the most important fossil we have from the early universe. They are the imprints of quantum fluctuations, the microscopic seeds of density that were inflated to cosmic size during the inflationary epoch. These seeds are the very reason we exist. They are the slight overdensities that gravity would later use to pull matter together, eventually forming every galaxy, star, and planet. The pattern of these spots, their size and distribution, is a direct reflection of the universe's fundamental geometric properties at that moment of first light. To decode this cosmic cipher, scientists use a powerful geometric tool called spherical harmonics. Think of it this way: the CMB is painted across the inside of a giant sphere, the celestial sphere that surrounds us. Describing its complex, modeled pattern requires a mathematical language that is perfectly suited to a sphere, much like how musical notes can be combined to describe any complex sound. Spherical harmonics are the notes in the universe's symphony. They allow cosmologists to break down the complex temperature map of the sky into its constituent parts, sorting the fluctuations by their angular size. Large-scale patterns, like giant ripples across the sky, correspond to low harmonic numbers, while finer, more detailed speckles correspond to higher numbers. This process creates what's called a power spectrum, a graph that plots the intensity of the fluctuations against their size. The shape of this graph is exquisitely sensitive to the geometric parameters of the universe. This is how we know, with remarkable precision, the fundamental geometry of our cosmos. The location of the first major peak in this power spectrum is a direct measure of the universe's curvature. A universe with positive curvature, like a sphere, would cause light rays to converge, making the spots appear larger. A universe with negative curvature, like a saddle, would make them appear smaller. The data from the CMB shows a very specific size for the largest spots, and it points conclusively to a universe that is flat, or very nearly so. This geometric flatness means that on the largest scales, the familiar rules of Euclidean geometry hold true. Parallel lines will never meet, and the angles of a triangle always add up to 180 degrees. This profound result tells us that the total density of the universe is at the critical value, balancing expansion and gravity in a way that defines its ultimate fate. Missions like the Planck satellite, launched by the European Space Agency, have given us this map in stunning, unprecedented detail. Planck spent years scanning the entire sky, measuring the CMB's temperature variations with microkelvin precision. The resulting map is a Rosetta Stone for cosmologists. By analyzing its geometric patterns through spherical harmonics, the Planck collaboration didn't just confirm the flatness of the universe. It also provided a precise inventory of its contents, determining that about 5% is ordinary matter, 27% is dark matter, and 68% is dark energy. It also gave us a highly accurate age for the universe, 13.8 billion years. Every wrinkle in that ancient light has been made to confess its secrets, revealing the geometric and physical conditions of the cosmos in its infancy. The CMB is far more than a static snapshot. It is a dynamic, information-rich time capsule. A direct message from the dawn of time that confirms the universe is built upon a foundation of elegant, understandable geometry. So we've seen how geometry imprinted itself on the infant universe and sculpted its large-scale structure. But this cosmic story is far from over. In fact, the plot has taken a dramatic and unexpected twist that is actively shaping the universe's ultimate fate. And once again, geometry is at the heart of the mystery. For most of the 20th century, cosmologists were locked in a debate between two possible futures for the cosmos: the Big Crunch, where gravity eventually halts expansion and pulls everything back into a fiery collapse, or the gradual, coasting expansion of a forever cooling universe. The geometry of the universe, specifically its curvature, was the key to deciding between these fates. A positively curved, closed universe would eventually collapse. A negatively curved, open universe would expand forever. A perfectly flat universe was the critical, knife-edge case, poised delicately between the two, destined to expand forever but at a rate that slowed to a crawl over eternity. Then, in the late 1990s, two independent teams of astronomers made a discovery that shattered this simple picture. They were measuring the distances to extremely far-off supernova exploding stars known as Type 1, a supernova, which serve as brilliant, standard candles for measuring cosmic distances. They expected to see that the expansion of the universe was slowing down as gravity steadily applied its brakes. Instead, they found the opposite. The most distant supernova were fainter than expected, meaning they were farther away than our models predicted. The expansion of the universe wasn't slowing down, it was speeding up. Some mysterious, repulsive force was pushing galaxies apart with ever-increasing vigor. This force was dubbed dark energy, and its discovery turned cosmology upside down, earning the researchers the Nobel Prize in Physics in 2011. But what does this have to do with geometry? Everything. Dark energy is directly woven into the geometric fabric of spacetime through a term in Einstein's equations called the cosmological constant, represented by the Greek letter lambda. Originally, Einstein introduced this constant as a kind of mathematical fudge factor to force his equations to describe a static, unchanging universe, which he and everyone else at the time believed in. He later called it his greatest blunder when Edwin Hubble discovered the universe was actually expanding. But with the discovery of acceleration, the cosmological constant was resurrected. It now represents the energy inherent to the vacuum of space itself, a constant energy density that, as the universe expands and creates more space, actually gains in strength relative to the weakening pull of matter. This constant has a specific geometric effect. It contributes to the overall curvature and fate of the universe. The measurements from those supernova, combined with the precise geometric data from the cosmic microwave background and the clustering of galaxies in the large-scale structure, all point to the same stunning conclusion. Our universe is flat or extremely close to it, and its composition is dominated by this dark energy, which makes up about 68% of its total energy budget. This geometric picture, painted by multiple independent lines of evidence, allows physicists to chart the possible destinies of the cosmos with newfound clarity. In our current best fit model, often called the lambda CDM model, dark energy in the form of a cosmological constant dooms the universe to a specific, rather lonely fate, the heat death or the big freeze. As the accelerated expansion continues, distant galaxies will be pushed beyond our observable horizon, their light never able to reach us again. Eventually, all galaxies outside our local group will vanish from sight. Star formation will cease as interstellar gas is blown apart and cannot coalesce. Existing stars will burn out, leaving behind cold stellar remnants like black holes, neutron stars, and white dwarfs. Over trillions upon trillions of years, even these remnants may evaporate through quantum processes, until the universe becomes a vast, ever-cooling, and nearly empty void, with a temperature asymptotically approaching absolute zero. The geometry of a flat, dark energy-dominated universe leads to this eternal, quiet expansion. But is this the only possibility? The nature of dark energy itself is still one of the biggest mysteries in physics. What if the cosmological constant isn't truly constant? What if this dark energy is something dynamic, a field that evolves over time, which cosmologists call quintessence? This opens up other geometric and dramatic possibilities. If this quintessence were to strengthen in a certain way, it could lead to a scenario known as the Big Rip. In this future, the repulsive force of dark energy grows without bound, eventually overcoming all other forces. It would first tear apart galaxy clusters, then individual galaxies. As the acceleration becomes infinitely strong, it would rip apart stars and planets, and finally, it would shred atoms and spacetime itself apart in a catastrophic end to the universe. Conversely, if dark energy were to somehow decay away or even become attractive, the pendulum could swing back the other way. Gravity could reassert its dominance, slowing the expansion, halting it, and finally reversing it. This would lead to the classic Big Crunch, a cosmic collapse back into a singularity. The geometry of the universe, dictated by the interplay between dark energy, matter, and curvature, is the map that charts the course between these vastly different destinies. It's a profound reminder that the shape of space is not a static backdrop. It is an active, dynamic participant in the cosmic story, holding the key to understanding not only where the universe has been, but where it is ultimately headed. While the geometric principles of general relativity beautifully describe the cosmos and its grand structures, they hit a formidable wall when confronted by the bizarre rules of the quantum world. At the subatomic scale, gravity as described by Einstein simply doesn't play nice with the probabilistic, fuzzy nature of quantum mechanics. For decades, physicists have searched for a theory that could bridge this divide, a single framework that could describe all forces and particles. One of the most ambitious and geometrically stunning proposals to emerge from this quest is string theory. This revolutionary idea suggests that the fundamental building blocks of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy strings. And to make this elegant idea mathematically consistent, string theory makes a breathtaking demand. The universe must have more than the three spatial dimensions and one time dimension we experience every day. It requires 10 or even 11 dimensions to work. This immediately raises an obvious and profound question. If there are all these extra dimensions, where are they? Why don't we see them? The answer provided by string theory is as ingenious as it is mind-bending. The theory proposes that these extra dimensions are not vast and expansive like the three we know. Instead, they are curled up or compactified into an astonishingly small space. How small? Roughly at the Planck scale, a size a billionth of a trillionth of a trillionth the size of an atomic nucleus. They are so tiny that no experiment we can currently conceive would be able to directly probe them. But their existence, and more importantly their specific geometric shape, is not a mere mathematical trick. It is absolutely everything. The way these extra dimensions are folded and curled determines how the fundamental strings within them can vibrate. And in string theory, the vibration of a string is its identity. One specific resonant frequency might correspond to an electron, another to a photon, another to a quark. The properties we assign to particles, their mass, their charge, their spin, all emerge from the geometric constraints of how a string can dance within this hidden, multidimensional space. The specific types of shapes that satisfy the demanding mathematical requirements of string theory are known as Calabi-Yau manifolds, named after the mathematicians Eugenio Calabi and Xing-Tung Yau. These are not simple shapes like spheres or donuts. They are intricate, multi-dimensional forms of breathtaking complexity and beauty. A Calabi-Yau manifold is a space with very specific properties, including what's known as SU3, holonomy, and a vanishing first Chern class, jargon that essentially means it possesses a very special and stable type of curvature that allows for the supersymmetry often required by the theory. To visualize one is nearly impossible for our three-dimensional brains, but we can glimpse a two-dimensional shadow of a six-dimensional Calabi-Yau shape, which often reveals an ornate structure full of holes, folds, and tunnels. The number of holes, known as the Hodge numbers, in this manifold is critically important. Each hole, each topological feature, influences the way strings can wrap around the geometry. Some strings might be stretched around a hole, while others might be looped through a tunnel. Each distinct way of interacting with the manifold's topology corresponds to a different vibrational mode, and therefore, a different kind of particle with different properties. In this breathtaking vision, the entire menagerie of particles that make up our universe, the electrons, the quarks, the neutrinos, the force carriers, are simply different notes on a geometric instrument. The universe is not a collection of things, but a symphony of vibrations played on the hidden strings of a Calabi-Yau manifold. To work with these extraordinary objects, string theorists must employ some of the most advanced tools in modern geometry. Algebraic topology is used to classify the shapes based on their invariant properties, like the number of holes, which cannot change if the shape is smoothly deformed. This helps physicists understand the fundamental topological constraints that different manifolds impose. Differential geometry and complex analysis are used to describe the precise curvature and intricate structure of these spaces at every single point. The mathematics is so sophisticated that it often leads to new discoveries in pure mathematics itself, creating a fascinating feedback loop between theoretical physics and abstract math. The ultimate goal is to find the one specific Calabi-Yau manifold, or the right class of them, whose geometry produces a vibrational spectrum that exactly matches the particle content and forces we observe in our universe. This is a monumental challenge, as there are potentially hundreds of thousands of mathematically possible Calabi-Yau shapes, leading to a vast landscape of possible universes, each with its own unique physical laws. This is where string theory, for all its geometric elegance, remains firmly in the realm of the speculative. No experimental evidence has yet been found to confirm the existence of extra dimensions or superstrings. The energy levels required to probe such tiny scales are far beyond the reach of our current particle accelerators. Furthermore, the theory's incredible flexibility, with its multitude of possible solutions, makes it difficult to pin down specific, testable predictions that would definitively prove it right or wrong. Despite these challenges, string theory stands as a monumental achievement in geometric thought. It represents the ultimate expression of the ancient intuition that geometry is the fundamental language of reality, pushing that idea to its logical extreme. It suggests that if we could only decipher the geometric code of the Calabi-Yau manifolds, we would hold the key to understanding everything, from the nature of gravity to the origin of matter itself, unifying the cosmos and the quantum in a single, harmonious geometric framework. But if string theory uses extra dimensions to unify physics, the holographic principle takes a radically different and almost paradoxical approach. It suggests that dimensions themselves might be an illusion, a projection from a simpler reality. This mind-bending idea emerged not from pure mathematics, but from a deep puzzle about black holes and information. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's event horizon, the point of no return, has a property that behaves exactly like entropy, a measure of disorder and information. Stephen Hawking later confirmed this by showing that black holes aren't completely black. They radiate energy and slowly evaporate due to quantum effects. This created a huge problem known as the black hole information paradox. If a black hole evaporates completely, what happens to all the information about the stars, gas, and matter that fell into it? Quantum mechanics says information can never be truly destroyed, so where does it go? The revolutionary solution, proposed by Gerard T. Hooft and Leonard Susskind, was that the information isn't lost inside the black hole. It never actually fell in. Instead, it is perfectly encoded, pixel by pixel, on the two-dimensional surface of the event horizon. Every bit of information about the three-dimensional volume inside the black hole is painted onto its two-dimensional boundary. The black hole, in essence, acts like a cosmic hard drive, with its surface area, not its volume, determining its maximum information storage capacity. This was the genesis of the holographic principle, an idea that suggests that for any region of space, all the information contained within it can be described by a theory that lives on its lower dimensional boundary. Our experience of a rich, three-dimensional world might be a magnificent illusion, a holographic projection from a vast, distant, two-dimensional surface. To make this abstract concept more concrete, think of an ordinary hologram. A holographic image on your credit card is a two-dimensional piece of film, but when you shine light through it, it projects a fully three-dimensional image that you can look around. The entire 3D image is encoded on the 2D surface. The holographic principle applies this same logic to the entire universe. The space we live in, with all its stars, planets, and people, could be a projection from a vast, complex boundary that surrounds us. The most well-developed example of this is the AD-S/CFT correspondence, discovered by Juan Maldacena. It proposes a precise mathematical duality, a kind of dictionary, between a type of universe with negative curvature called anti-de Sitter space, or AD-S, and a conformal field theory, or CFT, that lives on its boundary. The gravitational physics happening in the bulk of the AD-S space is completely equivalent to and encoded by the quantum physics happening on its boundary. A complex calculation involving gravity in a five-dimensional volume is exactly mirrored by a calculation involving quantum particles on a four-dimensional surface. This isn't just a vague analogy. It's a concrete mathematical equivalence that has provided physicists with powerful new tools to solve previously intractable problems in quantum gravity. This geometric duality fundamentally challenges our most basic notions of reality. It upends the classical idea of locality, the principle that objects are directly influenced only by their immediate surroundings. In a holographic universe, what happens here could be directly tied to a process happening on a remote boundary billions of light years away. It also turns our understanding of dimensionality on its head. We perceive ourselves as three-dimensional beings moving through time, but the holographic principle suggests this is an emergent property, not a fundamental one. The true, fundamental description of reality might require fewer dimensions, and our familiar 4D spacetime could be a derivative concept that arises from the interactions of quantum information on a lower dimensional surface. This blurs the line between the geometric fabric of spacetime and the abstract concept of information. It suggests that spacetime itself might not be a primary stage, but might be woven into existence by the entanglement of quantum bits of information. The universe, in this view, might not be made of stuff in a place, but of information itself, with geometry being the language in which that information is expressed. It's a profound and humbling idea that reimagines the cosmos not as a container of things, but as a dynamic, evolving projection of data, where the deepest laws of physics are ultimately about the flow and storage of information. While string theory adds extra dimensions and the holographic principle suggests dimensions may be an illusion, another profound approach to uniting gravity and quantum mechanics takes a dramatically different path. It asks a deceptively simple question: what if spacetime itself is not smooth and continuous, as Einstein described, but is instead granular, made of tiny, indivisible pieces? This is the core idea behind loop quantum gravity, a theory that dares to quantize the very fabric of reality. Just as quantum mechanics revealed that energy, light, and matter come in discrete packets called quanta, loop quantum gravity proposes that space and time themselves are pixelated. There is a smallest possible unit of space, a tiny quantum of volume, and a smallest possible unit of time, a quantum of time beyond which you cannot divide. This isn't a limitation of our measuring tools. It is a fundamental property of the universe, woven into its geometric core. The language this theory uses to describe this quantum spacetime is as beautiful as it is radical. It represents space not as an empty void, but as a vast, evolving network of relationships called a spin network. Imagine a magnificent cosmic graph, a web of nodes connected by links. Each node represents a tiny, discrete grain of space, a quantum of volume. Each link connecting the nodes represents the area that separates them. Crucially, these links are labeled with numbers called spins, which come from quantum mechanics. The value of these spin numbers on the links determines the precise area of the boundary between two grains of space, while the way the nodes are connected determines the volume of the grains themselves. In this breathtaking view, the space you are occupying right now is not fundamentally smooth. If you could peer down to the Planck scale, you would see a shimmering, dynamic network of these geometric atoms, buzzing with quantum uncertainty. The smooth, continuous space of our everyday experience is an emergent illusion, a kind of average over of this underlying microscopic chaos, much like a smooth piece of fabric emerges from the intricate weaving of individual threads. But a static network is only half the story. We live in a dynamic universe where spacetime curves and evolves. To account for this, the spin network itself must change over time. This is where the theory gets its name, loop quantum gravity. The evolution of the spin network is described by mathematical operations that create tiny loops or folds in the network. A single moment in time is a frozen snapshot of this spin network. The passage of time is then described by the transitions between these snapshots, as the network evolves from one configuration to another according to specific quantum rules. These transitions can be visualized as the network jiggling, with new nodes and links popping in and out of existence. A full history of this evolution creates a structure called a spin foam, a four-dimensional tapestry that represents spacetime itself, with the spin network slices representing space at each moment. This provides a complete, quantum mechanical description of geometry, where even the flow of time is reduced to a sequence of discrete, relational changes in the network. This radical reimagining of spacetime geometry has a powerful and elegant consequence. It naturally resolves the terrifying singularities that mark the breakdown of Einstein's equations. In general relativity, the center of a black hole is a point of infinite density and curvature, and the Big Bang is a moment where the universe was compressed into an infinitely small point. These are places where the mathematics simply gives up, screaming that the theory is incomplete. But in loop quantum gravity, there is no such thing as infinite density or zero volume because volume is quantized. You cannot squeeze matter into a space smaller than the smallest quantum of volume. This has led to a stunning prediction called the Big Bounce. Instead of the universe beginning from a singularity, loop quantum cosmology, the application of these ideas to the entire cosmos, suggests that our Big Bang was not a true beginning, but rather a rebound from a previous universe that had collapsed. As that previous universe contracted, it reached a point of maximum possible density, dictated by the quantum geometry, and then bounced outward into the expansion we see today. Similarly, the heart of a black hole might not be a point of infinite doom, but a bridge, a quantum tunnel of extreme but finite density, potentially leading to another region of spacetime. In this view, singularities are not the end of physics. They are merely artifacts of assuming spacetime is continuous when it is, in fact, granular. This perspective turns our conventional understanding of reality inside out. In Einstein's universe, space and time form the fixed, unchanging stage upon which the drama of particles and forces plays out. But in loop quantum gravity, the stage itself is built from the actors. Space and time are not fundamental. They are emergent properties that arise from the vast, tangled web of quantum relationships between these elementary grains. The geometry of the world is not a primary given. It is a consequence, a collective behavior that appears when we look at the spin network from a distance, much like the temperature and pressure of a gas emerge from the frantic motion of countless molecules. This is perhaps the most profound insight of all, that the familiar, comforting continuity of space and the steady flow of time are not the bedrock of reality. They are a convenient, large-scale approximation of a far stranger, more vibrant, and deeply geometric quantum world, humming just beneath the surface of our perception. All of these grand geometric features, the flatness of spacetime, the specific value of the cosmological constant, even the very number of spatial dimensions, appear to be exquisitely, almost miraculously, fine-tuned. Tweak any one of these parameters by even the tiniest fraction, and the entire cosmic project of building a universe capable of supporting life collapses. If the universe's density had been slightly higher after the Big Bang, that positive curvature would have caused it to recollapse into a big crunch long before stars could ever form. If the density had been slightly lower, the negative curvature would have led to such a rapid, runaway expansion that matter would have been blown apart, never able to coalesce into the first galaxies. The initial conditions had to be balanced on a knife's edge of geometric perfection for any of this to be possible. This delicate balancing act extends to the force of dark energy, encoded in the cosmological constant, lambda. The value we have measured is bizarrely small, yet crucially non-zero. If it were significantly larger, the repulsive force would have kicked in during the universe's infancy, violently tearing apart every nascent gravitational clump before planets, stars, or even atoms could ever assemble. The cosmic web would never have formed. Conversely, if dark energy were zero or negative, the universe might have collapsed long ago or expanded too slowly, potentially not allowing enough time for the complex, multi-billion-year processes of stellar nucleosynthesis and planetary formation to forge the heavy elements essential for life. Our universe's specific geometric recipe seems to have been perfectly calibrated to allow for both the formation of large-scale structure and its long-term evolution, creating a stable, habitable platform over immense cosmic timescales. Faced with this staggering improbability, this apparent cosmic coincidence, scientists and philosophers have proposed a compelling and deeply controversial explanation: the Anthropic Principle. In its simplest form, it states that the universe, Chinese letter, 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 Chinese letter. We could not possibly find ourselves in a universe that is incompatible with our own existence. The geometry is flat, and the cosmological constant is small not because of some fundamental law dictating it must be so, but because this is one of the very rare combinations of parameters that permits the emergence of conscious life to observe it. In this view, the fine-tuning isn't a puzzle to be solved by a deeper theory of everything, but a selection effect. We are here, so the universe must be this way. This idea immediately sparks a fierce and fascinating debate about what this fine-tuning implies. Is it simply a monumental stroke of luck, a random roll of the cosmic dice that happened to land on a winning combination? This seems almost impossibly unlikely. Does it point toward some form of necessity, a deeper, undiscovered physical law that logically forces these constants to have the values they do, making a life-permitting universe inevitable? Or does it hint at something even more profound, like the existence of a multiverse? In a vast or infinite multiverse, every possible combination of physical constants and geometric parameters is realized in different pocket universes. We naturally find ourselves in one of the exceedingly rare universes where the numbers are just right for life, simply because we couldn't exist anywhere else. In this scenario, our universe's geometry isn't special. It's just the one we won the lottery to live in. The Anthropic Principle powerfully connects the abstract mathematics of cosmology to the concrete reality of our own existence. It suggests that the reason we can contemplate the perfect symmetry of a dodecahedron or the curved spacetime around a black hole is because the overarching geometry of our entire cosmos provided a nursery stable and long-lived enough for that contemplation to evolve. The geometric parameters are not cold, remote numbers in an equation. They are the foundational settings that made galaxies, stars, planets, and ultimately us possible. They are the silent, non-negotiable prerequisites for a universe that has a story to tell and conscious beings to hear it. Whether this is seen as a tautology, a profound insight, or a philosophical cop-out, the Anthropic Principle forces us to confront the astonishing fact that the laws of geometry are inextricably linked to the possibility of life itself, blurring the line between the language of physics and the conditions for being. We've explored the universe's curvature, but there's an even deeper geometric question lurking in the background, one that challenges our most basic intuition about space itself. Is the cosmos truly infinite, stretching on forever in all directions, or could it be finite, yet without any boundary or edge? This isn't a question of what the universe is made of, but of its overall shape, its topology. While general relativity tells us about the local curvature of spacetime, topology deals with the global structure, the overall connectedness of the cosmos. It asks whether space might wrap around on itself in some clever, compact way, making the universe finite but utterly unbounded. Imagine an ant on the surface of a donut, or a video game character who exits the screen on the right only to immediately reappear on the left. The space they navigate is finite. They could eventually traverse every part of it, but there is no edge, no center, and no boundary. The entire universe could, in principle, be structured the same way. One of the most compelling finite models is known as the Poincare dodecahedral space. This is a profoundly beautiful and complex geometric shape. Picture the familiar 12-sided die from a role-playing game, a dodecahedron. Now imagine that each of its pentagonal faces is connected to the opposite face, but with a twist, literally. When you pass through one face, you don't just emerge from the opposite one. You re-enter the space from a different, rotated orientation. This creates a finite, multiply-connected space that is perfectly consistent with a flat universe. Light would travel in straight lines, but because space wraps around, a beam of light could, in theory, eventually return to its starting point from the opposite direction. If this model were correct, the entire cosmos would be a kind of cosmic hall of mirrors, but on such an immense scale that we wouldn't notice the repetition in our everyday lives. Another simpler, though still mind-bending, model is the three torus. Imagine a cube where, again, each face is connected to the one opposite it. If you fly a spaceship straight up, you'd eventually find yourself coming up from the bottom. Go far enough to the right, and you reappear on the left. This creates a finite volume with the geometry of a flat plane, but with a periodic structure. It's a perfectly valid solution to Einstein's equations, and it would mean the universe, while incredibly vast, is not infinite. So how could we possibly test such an extraordinary idea? The key is to look for the ghostly imprints this wrapping of space would leave on the oldest light. We can see the cosmic microwave background. If the universe is finite and multiply connected, then the space itself is smaller than the distance light has traveled since the Big Bang. This means that light rays could have wrapped around the entire cosmos multiple times. The consequence of this is that when we look at the CMB, we might see the same patch of sky repeated in different directions. It would be like standing in a room lined with mirrors and seeing infinite reflections of yourself. Cosmologists have meticulously searched for these telltale signs, most famously by looking for matched circles in the CMB. The idea is that if the universe has a non-trivial topology, we might see pairs of circles in the microwave sky that have identical patterns of hot and cold spots. These circles would be the signature of a single ancient ripple in spacetime, whose light has taken two different paths around the universe to reach us, creating a double image. This search is incredibly difficult. The universe is overwhelmingly vast, and any repeating patterns would be faint and stretched across billions of light years. Furthermore, the expansion of the universe and the process of inflation have likely stretched space so much that any topological features would be on a scale larger than our observable horizon, making them effectively undetectable. So far, exhaustive analyses of data from the Planck satellite and other observatories have not found any convincing evidence for these matched circles. The current data is most consistent with a universe that is simply connected, meaning it either is truly infinite, or it is so large that its finite size is beyond our observable reach. Yet, the search continues because the implications are so profound. Discovering that the universe is finite would be one of the most staggering revelations in the history of science. It would redefine our place in the cosmos, transforming the universe from an endless, anonymous void into a single, cohesive geometric object with a specific shape and size, a cosmic habitat with a knowable architecture. It reminds us that the true nature of reality often lies beyond our everyday intuition, hidden in the elegant and sometimes baffling language of geometry. Yet for all its geometric elegance, Einstein's theory of general relativity presents physicists with a formidable challenge. Its equations are breathtakingly complex, a tangled web of non-linear partial differential equations that describe the dynamic dance of spacetime curvature. For simple systems like a single star, these equations can be solved by hand, yielding elegant solutions like the Schwarzschild metric. But for the most dramatic events in the cosmos, the violent collision of two black holes, the cataclysmic explosion of a neutron-star merger, the mathematics becomes impossibly difficult. The sheer, raw power of these events warps spacetime so severely that no pen and paper calculation can hope to capture the true, chaotic geometry of the outcome. To understand these extreme environments, scientists had to invent an entirely new discipline, one that marries the abstract beauty of geometry with the raw computational power of modern supercomputers. This field is called numerical relativity, and it allows us to do the seemingly impossible, to solve Einstein's equations by transforming the smooth fabric of spacetime into a vast digital grid. The core challenge is taking the continuous, dynamic geometry described by general relativity and translating it into a language a computer can understand. Computers deal in discrete numbers, not smooth curves. So, numerical relativists begin by slicing the four-dimensional continuum of spacetime into a three-dimensional spatial grid that evolves over discrete time steps. This process, known as discretization, creates a computational mesh, a gigantic, evolving lattice of points where the equations of gravity are solved step by step. But this is no simple cube. The geometry around a black hole is wildly distorted, requiring a mesh that can adapt in real time, concentrating computational power in regions of extreme curvature and coarsening in calmer areas. This relies heavily on advanced computational geometry to create these adaptive grids, ensuring that the simulation remains stable and accurate even as black holes spiral inward and merge, sending powerful ripples through the computational domain. Handling the infamous singularities at the hearts of black holes is another monumental geometric feat. Rather than trying to calculate the infinite curvature itself, which would crash any simulation, scientists use clever coordinate transformations. They effectively stretch and smooth the geometry near the singularity, like a cartographer finding a new projection to map the poles of a globe without distortion, allowing the simulation to evolve the entire system without getting sucked into the mathematical abyss. The ultimate triumph of this decades-long computational effort came on September 14, 2015, when the LIGO Observatory made the first direct detection of gravitational waves, ripples in spacetime from a black hole merger over 1 billion light-years away. That momentous discovery was not a solo act. It was a duet between experimentalists and numerical relativists. For years leading up to the detection, teams around the world had been running immense simulations on the world's most powerful supercomputers, calculating the precise gravitational waveform, the specific pattern of stretching and squeezing of spacetime, that would be produced by two colliding black holes. These simulations generated a vast library of template waveforms, a catalog of possible cosmic signatures. When LIGO instruments caught that faint chirp from the depths of space, researchers cross-referenced it against these pre-computed templates. The signal matched the predictions from numerical relativity with stunning accuracy, confirming not only the existence of gravitational waves, but also providing direct, observational proof that black holes merge exactly as Einstein's theory and supercomputer simulations said they would. Without those detailed geometric simulations, the signal might have been dismissed as noise. With them, it became a precise tool for cosmic measurement, allowing scientists to determine the masses and spins of the black holes involved. This success has opened a new window onto the universe, transforming gravitational wave astronomy from a theoretical possibility into a routine observational tool. Every new detection of a collision between black holes, neutron stars, or a mix of both is now accompanied by a flurry of sophisticated simulations. By comparing the observed waves to the simulated ones, scientists can reverse engineer the geometry of these cataclysmic events, inferring the properties of the most exotic objects in the universe with incredible precision. The simulations have revealed fascinating details, like the final ring-down phase after a black hole merger, where the newly formed, distorted black hole vibrates like a struck bell, settling into a perfectly smooth horizon dictated by the Kerr metric. They have also been crucial for interpreting the multi-messenger event of a neutron-star merger, where simulations of the extreme geometry helped predict the behavior of the ejected material that glowed with light across the electromagnetic spectrum. Numerical relativity has taken geometry out of the textbook and turned it into a practical engineering tool, a digital laboratory for testing the limits of gravity and exploring the most violent and energetic events since the Big Bang itself, all from the safety of a computer cluster. Einstein's geometric vision of gravity gave us a universe where mass tells spacetime how to curve, but it also gave us a remarkable new way to see that universe, by watching how light itself bends and twists as it travels through the warped cosmic landscape. This phenomenon is called gravitational lensing, and it is one of the most direct and dramatic demonstrations that geometry isn't just an abstract concept. It actively shapes our view of the cosmos, acting as a natural magnifying glass and a powerful tool for discovery. The principle is beautifully simple, yet its implications are profound. Imagine a beam of light from a distant quasar or galaxy traveling across the universe for billions of years, following what it believes is a straight line through the void. But if its path takes it near a massive object, a galaxy cluster, or a black hole, it enters a region where spacetime itself is curved. In this distorted geometric terrain, the straightest possible path, known as a null geodesic, is no longer the line we would draw on a flat map. It's a curve, bending around the massive object like a car following the banked curve of a racetrack. From our perspective, the light appears to be coming from a different direction than its true source, creating a cosmic illusion that can magnify, distort, and even multiply the image of the distant object. This bending of light leads to several spectacular geometric patterns in the sky. The simplest form is called weak lensing, where the image of a background galaxy is subtly stretched and sheared, its shape distorted into a tiny arc. While this might seem like a minor effect, it becomes incredibly powerful when we look at thousands of galaxies behind a massive cluster. Their collective distortion paints a clear picture of the warped spacetime they all pass through, allowing astronomers to literally map the gravitational field of the foreground cluster. A more dramatic and visually striking effect is strong lensing. When the alignment between the foreground mass, the observer, and the background source is nearly perfect, the bending of light can create multiple distinct images of the same object, or wrap the light into a complete or partial circle known as an Einstein ring. These rings and multiple images are not just beautiful curiosities, they are precise geometric constructions. The size and shape of an Einstein ring depend directly on the mass of the foreground object and the alignment geometry, providing a cosmic scale that astronomers can use to weigh galaxies and clusters with extraordinary accuracy. In the most extreme cases, like the light from a star passing very close to a compact object, we get microlensing, where the brightness of the star is temporarily magnified as the gravitational curvature acts like a focusing lens. A fleeting event that can reveal otherwise invisible objects like rogue planets or stellar mass black holes. But the true power of gravitational lensing extends far beyond creating pretty pictures. It has become one of astronomy's most indispensable tools, a cosmic telescope that nature itself provides. Because the amount of light bending depends on the total mass warping spacetime, lensing allows us to see the invisible. We can now map the distribution of dark matter within galaxy clusters with stunning detail. By analyzing the intricate patterns of distorted background galaxies, scientists can create a mass map of the intervening cluster, revealing how this mysterious, invisible substance is structured. These maps consistently show that dark matter forms a massive, diffuse halo that extends far beyond the visible stars, providing some of the most compelling evidence for its existence and helping us understand how it governs the growth of cosmic structure. Furthermore, lensing provides a crucial test for general relativity itself. The theory makes very specific predictions about how much light should bend for a given mass. By carefully measuring the positions and brightnesses of multiple images and arcs, astronomers can check if Einstein's equations hold true over vast cosmic distances and in the incredibly strong gravity of galaxy clusters. So far, they have passed every test with flying colors, cementing the geometric view of gravity as the correct description of our universe. Perhaps the most profound implication of gravitational lensing is that it forces us to confront the fact that we never see the universe directly. We see it through the filter of geometry. The light that reaches our telescopes has been on an epic journey through a space-time landscape that is anything but flat and empty. It has been stretched by the overall expansion of the universe, redshifted by gravity, and bent by every bit of matter it passed along the way. Our view of the sky is a distorted projection, a cosmic carnival mirror that gravitational lensing allows us to understand and correct for. By learning to read these distortions, we don't just see more deeply into space. We decode the very shape of the space itself, using light as a probe to measure the invisible architecture of mass that defines the cosmos. It is a perfect example of how geometry is not just a language we use to describe the universe, but the fundamental medium through which the universe communicates its secrets to us. But if the geometry of our own universe feels vast and complex, the multiverse hypothesis pushes that concept to its absolute limit, proposing that every possible geometric configuration of reality might actually exist somewhere in a grander, meta-cosmic ensemble. This isn't science fiction. It's a serious, though speculative, extension of our most successful physical theories. The idea emerges from a fascinating convergence of cosmology and string theory, each pointing toward a reality far grander and more varied than the single universe we call home. In this breathtaking view, our universe, with its specific flat geometry, three spatial dimensions and finely tuned constants, might be just one page in an infinite library of universes, each volume written with a different set of geometric rules. One of the most compelling pathways to this multiverse is through the mechanism of eternal inflation. Recall that cosmic inflation is the theory of a rapid, exponential expansion driven by a high-energy scalar field. Eternal inflation suggests that this process might never truly stop everywhere at once. Imagine a vast, bubbling ocean of primordial, high-energy spacetime. In most regions, the inflattened field eventually rolls down its potential hill, inflation ends, and that region settles into a stable, low-energy state, becoming what we would recognize as a universe like our own, a localized bubble in the greater meta-cosmic foam. But due to quantum fluctuations, some regions of this frothing sea remain stuck in the high-energy inflationary state. These regions continue to expand at a furious, exponential rate, constantly creating new volume. Within this ever-inflating background, an infinite number of bubble universes can nucleate, each one potentially with different properties. Crucially, when each bubble forms, the way the inflattened field settles, the specific valley it rolls into, can determine the local laws of physics within that bubble, including the effective value of the cosmological constant and the number of dimensions that stabilize and become large. In this scenario, the geometric properties of each universe are essentially frozen accidents, a random outcome of how inflation ended in that particular pocket of reality. String theory offers another, even more geometrically rich pathway to the multiverse through what is known as the string theory landscape. As we explored, string theory requires extra dimensions to be compactified into intricate Calabi-Yau manifolds. The problem, or perhaps the feature, is that there isn't just one unique Calabi-Yau shape. There are a staggering number of possibilities. Estimates range from 10 to the 500 up to 10 to the 270,000 different viable configurations. Each distinct Calabi-Yau manifold, with its unique topology and number of holes, defines a different possible vacuum state, a different stable low-energy configuration for a universe. The specific geometry of the chosen manifold dictates the physical laws that emerge, the number of generations of particles, the strengths of the fundamental forces, and even the value of the cosmological constant. The landscape, is the vast collection of all these possible geometric configurations. The theory suggests our universe corresponds to one specific point in this landscape, one particular Calabi-Yau shape that yields the physics we observe. But if the mechanisms of eternal inflation are at play, then the greater cosmos could be populated by bubbles where the compactification has settled into any one of these myriad possibilities. We find ourselves in a universe compatible with life not because it's special, but because it's one of the few where the geometric dice landed in a habitable configuration. This is where geometry becomes destiny on a cosmic scale. The geometric properties of each universe in this vast multiverse would irrevocably determine its character and fate. A universe with a positive curvature might collapse in a big crunch before the first stars even form. One with a strong negative curvature would expand so rapidly that matter would be diluted into a thin, useless haze. A universe where the compactified dimensions resulted in a much stronger strong nuclear force might have all hydrogen nuclei fuse instantly after the Big Bang, leaving no fuel for stars. Another might have a cosmological constant 100 times larger than ours, causing a violent big rip that shreds reality in its infancy. The number of large spatial dimensions is perhaps the most fundamental geometric property of all. In a two-dimensional universe, the complex neural networks required for consciousness might be impossible to construct. In a universe with 4 large spatial dimensions, the laws of gravity and planetary orbits would be wildly different, likely preventing the formation of stable solar systems. Our universe's particular geometric recipe, 3 stable, expanding dimensions, a near-flat curvature, and a small cosmological constant appears to be a very specific and rare combination that allows for galaxies, stars, planets, and ultimately, life to emerge. The multiverse hypothesis provides a powerful, if controversial, framework for explaining this apparent fine-tuning. In an infinite array of universes, all possible geometries are realized, and we naturally find ourselves within one that can support our existence. This idea stretches the human mind to its limits, challenging us to conceive of geometry not as the fixed stage of our reality, but as a variable, fluid property that can change from one cosmic domain to the next. It transforms the question of why is our universe the way it is, from a question of fundamental law to a question of statistical selection in a possibly infinite ensemble. While the multiverse remains firmly in the realm of theoretical physics, a majestic and compelling extrapolation, rather than a proven fact, it represents the ultimate expression of the geometric viewpoint. It suggests that the language of shapes, dimensions, and curvature is not just the language of our cosmos, but the fundamental syntax of all possible realities, a timeless and infinite tapestry woven from the deepest principles of mathematics and physics. We stand at a remarkable crossroads in our quest to understand the cosmos, armed with both revolutionary new tools and revolutionary new ideas, all pointing toward a future where geometry is the primary lens through which we decipher reality. This new era is being ushered in by a fleet of next-generation observatories, instruments of such breathtaking precision they will allow us to measure the universe's geometric properties with an accuracy that was pure fantasy just a generation ago. Leading this charge is the James Webb Space Telescope, an engineering marvel that acts as a powerful time machine. By peering back to the very first galaxies that flickered into existence, Webb is not just showing us ancient stars. It is providing crucial data on how the cosmic web initially formed. By meticulously measuring the shapes and distributions of these infant galaxies, we can trace the invisible scaffolding of dark matter that guided their growth, testing our geometric models of gravitational collapse on the largest possible scale. Every distant galaxy cluster it observes is another data point in our map of the cosmic curvature. But Webb is just one part of a much larger geometric survey of the sky. The European Space Agency's Euclid spacecraft represents a more targeted mission, one designed with a single, profound geometric purpose: to create the largest and most precise 3D map of the universe ever made. It will achieve this by observing billions of galaxies across 10 billion light-years of space, measuring their shapes and positions with exquisite detail. Why is this so important? Because of weak gravitational lensing. As the light from these distant galaxies travels through the cosmos, its path is subtly bent and sheared by all the matter, both visible and dark, that lies between them and us. Euclid will detect these tiny, telltale distortions in the shapes of galaxies, allowing scientists to construct an enormous chart of how matter is distributed throughout the universe. This distribution is the direct result of the interplay between dark matter's gravitational pull and dark energy's repulsive push. By mapping the geometry of this matter web in 3 dimensions and across cosmic time, Euclid will measure the strength of dark energy and how it has changed over the history of the universe, effectively weighing the very fabric of spacetime itself to determine our ultimate cosmic fate. And the exploration doesn't stop with light. The Laser Interferometer Space Antenna, or LISA, is a future mission that will open an entirely new window onto the geometric universe by detecting gravitational waves from space. Unlike ground-based observatories like LIGO that catch the high-frequency chirps of stellar mass black holes, LISA will consist of 3 spacecraft flying in a giant triangular formation, millions of kilometers apart. It will sense the low-frequency ripples in spacetime caused by the mergers of supermassive black holes at the hearts of galaxies. These waves are a direct probe of dynamic geometry, carrying encoded information about the event horizons and the spacetime curvature around these colossal objects. By studying their waveforms, we can perform precision tests of general relativity in its most extreme regime, potentially uncovering deviations that point toward new physics. Furthermore, LISA might even detect a faint, stochastic background of gravitational waves from the first moments after the Big Bang, a literal echo from the birth of spacetime, offering us a glimpse into the primordial geometric state that inflation theory predicts. While these telescopes scan the skies, theoretical physicists are engaged in their own profound revolution, crafting new geometric concepts that could redefine our understanding of reality itself. In the world of particle physics, a fascinating new object called the amplituhedron is challenging centuries-old assumptions about how we calculate particle interactions. Traditionally, these calculations, which are essential for comparing theory to experiments at particle colliders, have been incredibly complex and involved thousands of tedious Feynman diagrams. The amplituhedron, a multi-dimensional geometric shape, bypasses this complexity entirely. It suggests that the probabilities for particle collisions are actually encoded in the volume of this abstract geometric object. This is more than a mathematical shortcut. It hints that the fundamental laws of physics might be deeply rooted in a geometric structure where concepts like locality and unitarity, the idea that events happen in a specific place and time, and that probabilities must add up to 1, are not fundamental but emergent properties. The amplituhedron points toward a universe where the geometry of abstract mathematical spaces is more fundamental than the spacetime we inhabit. This idea of emergence is also at the heart of other cutting-edge theories, like those based on quantum entanglement. Some physicists are now exploring the possibility that spacetime itself is not a foundational building block of the universe, but a phenomenon that emerges from the quantum entanglement of countless tiny bits of information. In this view, the smooth, continuous geometry described by Einstein is a large-scale illusion, a collective behavior that arises from a vast network of quantum connections. The connectivity between these quantum elements gives rise to the familiar dimensions of space and the flow of time. This is a radical geometric inversion, Instead of spacetime being the stage on which particles interact, spacetime is the performance, and the actors are the entangled quantum states. This framework offers a promising path to resolving the singularities that plague our current theories. In an emergent spacetime, the infinite curvature at the heart of a black hole or the beginning of the Big Bang simply cannot exist. There is no smooth continuum to become infinitely curved. Instead, the microscopic quantum geometry would take over, suggesting a bounce or a transition rather than a true singularity. Together, these experimental and theoretical advances are converging on the deepest mysteries in cosmology. The precise geometric data from Euclid and other surveys could finally reveal the true nature of dark matter by showing exactly how it clumps and interacts with itself, potentially distinguishing between different theoretical candidates. The observation of primordial gravitational waves by future observatories would be the ultimate smoking gun for cosmic inflation, providing direct evidence for that explosive geometric expansion. And new theoretical frameworks could finally reconcile the geometric picture of gravity with the quantum world, giving us a complete theory of quantum gravity. The path forward is filled with both immense promise and profound perplexity. Each new answer will undoubtedly unveil new, deeper questions about the geometric underpinnings of our universe. Yet one thing is certain: the future of cosmology will be written in the language of geometry, a language we are only just beginning to learn how to read. This profound journey through the geometric universe inevitably leads us to a question that is as ancient as philosophy itself, yet feels more urgent than ever in light of modern physics. Are the geometric truths we've been exploring the perfect symmetry of the Platonic solids, the curved fabric of spacetime, the intricate patterns of the cosmic web waiting out there in the universe to be discovered? Or are they elegant inventions of the human mind, a kind of conceptual lens we've crafted that just happens to fit the world around us with uncanny precision? This isn't just an abstract academic debate. The answer you lean toward shapes your entire conception of reality, of our place in the cosmos, and of the very nature of truth. On one side of this divide stands Plato, the original inspiration for so much of this geometric thinking. His philosophy of idealism argued that the perfect geometric forms we conceive of in mathematics, the ideal circle, the flawless triangle, the exact cube, are not abstractions we create. He believed they are real, eternal entities that exist in a perfect, non-physical realm of pure forms. The circles we draw in the sand or the crystals we dig from the earth are merely imperfect, shadowy reflections of these perfect, transcendent ideals. In this view, the mathematician and the physicist are like explorers, discovering pre-existing truths about the universe's fundamental architecture. When Johannes Kepler searched for geometric harmony in the solar system, he was operating as a Platonic idealist, convinced he was uncovering a divine geometric plan that was already there, written into the cosmos long before humanity existed to notice it. A radically different perspective emerged much later, with thinkers who argued that geometry is not discovered, but invented. This empirical view holds that geometric rules are generalizations we make from our experience of the physical world. We invented the concept of a straight line by observing the path of light or stretching a taut string. We deduced the properties of a circle by looking at the moon or tracing the rim of a cup. From these observations, we built up a system of rules, Euclidean geometry, that worked very well for building pyramids, navigating ships, and planning cities. But its authority, in this view, comes from its utility and its origin in sensory experience, not from it representing some transcendent truth. If we had evolved in a wildly different environment, we might have invented a completely different and equally useful geometric system. The philosopher Immanuel Kant attempted a fascinating synthesis of these two opposing views. He proposed that while our knowledge of the world comes from our sensory experience, The framework we use to organize that experience is hardwired into our minds beforehand. He argued that space and time are not things we discover in the world, but are the fundamental forms of our intuition, the necessary lenses through which we must perceive everything. We cannot help but see the world in terms of spatial relationships and temporal sequences. Therefore, the geometry we use for Kant is a priori. It's a precondition for having any experience at all. It is both discovered, in the sense that it's a necessary feature of reality as we perceive it, and invented, in the sense that it is a fundamental structure of the human mind itself. We can no more see outside of space and time than a fish can perceive being wet. Modern physics has explosively revitalized this centuries-old debate, pulling it from the pages of philosophy texts and into the heart of cutting-edge cosmology. The fact that we can use non-Euclidean geometry, a system invented by mathematicians purely by playing with logical alternatives to Euclid's postulates, to then accurately describe the curvature of the universe around black holes or the overall shape of the cosmos, is a staggering fact that begs for an explanation. It feels like too much of a coincidence. It suggests that our inventions have an eerie, pre-existing correspondence with physical reality. This unreasonable effectiveness of mathematics, as physicist Eugene Wigner called it, often feels like a powerful argument for the Platonic view. It seems we are indeed discovering something real. Yet, the direction of modern physics also leans into the inventive side of the coin. Our most ambitious theories, like string theory with its 10,000 possible Calabi-Yau manifolds, present us with a landscape of potential mathematical universes. We then must go out and discover which one corresponds to our own. The geometry isn't just sitting there waiting. We are actively constructing elaborate mathematical possibilities and then seeing if the universe matches one. Furthermore, the holographic principle profoundly blurs the line between invention and discovery. If our three-dimensional reality is a projection from a two-dimensional boundary, then the geometry we experience is literally a constructed illusion, a computational output. We invented the mathematics to describe the lower dimensional boundary, and in doing so, we discovered that the higher dimensional world we live in emerges from it. This suggests a universe where the deepest reality might not be geometric at all, but informational, with geometry being the beautiful, invented language it uses to express itself. So where does this leave us? Perhaps the most satisfying answer is that geometry is a magnificent and ongoing dialogue between the human mind and the universe. We invent mathematical concepts, pushing the boundaries of abstract thought and logical consistency. We then take these inventions and cast them out into the world like nets to see what they can catch. Sometimes the nets come back empty, but sometimes they pull in something miraculous. A pulsar timing exactly according to Riemannian curvature, a galactic cluster bending light into an Einstein ring, a subatomic particle matching a prediction from group theory. In those moments of breathtaking alignment, invention and discovery become inseparable. We are not just passive observers of a geometric cosmos, nor are we solitary inventors of a geometric fantasy. We are active participants in a universe that is not only written in the language of geometry, but is also capable of being read by a mind that can speak that very same language. This partnership between the structure of our minds and the structure of the cosmos may be the most profound geometric truth of all. Imagine a classroom not with rows of desks, but with students gathered around a large, intricate model they built themselves, a geodesic dome based on the geometry of an icosahedron, its triangular faces strong and stable. This hands-on experience does more than just teach them about shapes. It connects them to the same geometric principles that architect Buckminster Fuller used in his designs and that scientists see in everything from virus capsids to the large-scale structure of the universe. This is the power of bringing cosmic geometry into education. It transforms abstract, often intimidating concepts into tangible, thrilling discoveries. By using physical models, digital simulations, and interdisciplinary projects, educators can unlock a sense of wonder in students, showing them that the language of the cosmos isn't reserved for PhDs in astrophysics. It's a story they can begin to read and understand right now. One of the most effective ways to start this journey is by introducing the timeless elegance of the Platonic solids. These 5 perfect shapes are more than just mathematical curiosities. They are perfect hands-on teaching tools. A teacher might pass around a wooden dodecahedron, its 12 pentagonal faces feeling mysterious and ancient in a student's hands. They can discuss how Plato linked it to the heavens, and then seamlessly transition to a modern context, showing how the same geometry appears in the molecular structure of certain quasi-crystals, or in the way some viruses assemble their protective shells. Suddenly, that abstract shape is a bridge spanning thousands of years, connecting philosophy to biology and material science. Students can then be challenged to build their own Platonic solids using straws and pipe cleaners, learning about vertices, edges, and faces through direct experience. This kinesthetic learning cements the concepts far more effectively than any textbook diagram could, making the perfect symmetry of these forms a personal discovery. For concepts that are too vast or too small to hold in your hand, technology offers a window. Interactive gravity simulations are a game changer. A student can sit at a computer and set up their own virtual solar system, placing a sun and a few planets, then adjusting their masses and velocities. They hit run and watch with fascination as their planets either settle into stable elliptical orbits or go careening off into the void. This trial-and-error process teaches the principles of orbital mechanics and gravitational curvature in a way that is immediate and unforgettable. They aren't just memorizing Kepler's laws, they are discovering them. Similarly, software that visualizes the gravitational lensing around a virtual black hole can make Einstein's complex ideas about warped spacetime visually intuitive. Students can see how a background star's image stretches into an arc as it passes behind the black hole, directly observing how mass tells spacetime how to curve. These simulations make students active participants in the process of scientific inquiry. The artistic side of geometry provides another powerful entry point, particularly through the study of fractals. Fractal art projects are a brilliant way to merge math with creativity. A class might start by learning about the simple mathematical rule behind the Mandelbrot set. A complex number is squared and added to itself over and over again. Then, using freely available software, they can zoom into this infinite complexity, watching as the same intricate patterns repeat at every scale. They can then create their own fractal art, perhaps by drawing a simple branching pattern, and then repeating it recursively to create a tree that looks eerily real. This activity teaches them about recursion, self-similarity, and exponential growth. But it also shows them that what we often call chaos in nature, the shape of a cloud, the branching of a river delta, the structure of our lungs, often has a hidden, underlying geometric order. It demonstrates that math is not just about cold equations, but about the beautiful patterns that weave through our world. The ultimate goal of these educational strategies is to break down the artificial barriers between subjects. A truly interdisciplinary project might task students with a cosmic blueprint challenge. They could use geometry to design a stable structure for a Mars habitat, considering the strength of different shapes under low atmospheric pressure. They could study the physics of star formation by examining the fractal density patterns in a simulated nebula. They could analyze the mathematical proportions in the harmonic orbits of exoplanets, searching for patterns that might hint at stability and the potential for life. This approach shows students that to solve the big questions, you cannot rely on just one field of knowledge. You need the precise language of mathematics, the exploratory power of physics, the context of chemistry, and the creative thinking of engineering. Geometry becomes the unifying thread that ties it all together, the common syntax in the story of the universe. By making cosmic geometry accessible and engaging, we do more than just improve test scores. We foster a sense of cosmic connectedness and intellectual curiosity that can last a lifetime. A student who has built a model of a black hole's gravity well, or who has painted their own fractal galaxy gains a new lens through which to see the world. They start to recognize the octahedral symmetry in a perfectly formed diamond crystal and the hyperbolic geometry of a curly kale leaf. They understand that the same forces shaping the spin of a galaxy are also at work in the swirling water going down a drain. This demystifies the universe, making its wonders feel not distant and incomprehensible, but knowable and intimately connected to our daily lives. It empowers them with the profound realization that they, too, can learn to speak the universe's native language. Inspiring this generation of young explorers, tinkerers, and thinkers ensures that the relentless human quest to understand the hidden patterns of reality will continue, driven by the same awe that captivated Plato and Kepler, now armed with the tools and imagination to go even further. From the perfect forms envisioned by Plato to the vast cosmic web revealed by our most powerful telescopes, we have traveled across an astonishing landscape where geometry serves as the universal language, the hidden code that deciphers the cosmos's deepest secrets. This journey has taken us from the atomic scale, where the arrangement of a salt crystal echoes an ancient Greek ideal, to the very edge of observable reality, where the gravitational curvature of spacetime dictates the fate of everything. We have seen how geometric principles are not merely human inventions for describing the world, but are active, dynamic forces that shape everything from the spin of an electron to the majestic dance of colliding black holes. This exploration has woven together threads from physics, philosophy, and mathematics, revealing a cosmos that is far more structured, interconnected, and mathematically beautiful than we could have ever imagined. This geometric perspective fundamentally reshapes our understanding of our place within this grand scheme. We are not passive observers in a random, chaotic void. We are inhabitants of a universe that operates according to a profound and elegant order, an order written in the language of angles, symmetries, and dimensions. The same geometric rules that ensure the stability of a diamond on Earth also govern the formation of spiral arms in a galaxy millions of light-years away. The gravitational lensing that bends the light from a distant quasar operates on the same geometric principles that a child intuitively grasps when using a magnifying glass to focus sunlight. This realization fosters a powerful sense of connection, a cosmic kinship with the universe itself. We are beginning to understand that to learn the grammar of geometry is to learn how to read the story of the cosmos, a story in which we are both the readers and a fascinating, emergent chapter. As our tools of discovery grow ever more sophisticated, from space telescopes like James Webb and Euclid to gravitational wave observatories like LIGO and the future LISA mission, our geometric map of reality will only become richer and more detailed. We will peer deeper into the gravitational wells of black holes, probe the possibility of extra dimensions, and perhaps one day even witness the quantum geometric fabric of spacetime itself. The journey is far from over. In many ways, it has just begun. Each new answer unravels a dozen new questions, each more thrilling than the last. The greatest mystery may yet be why our human minds, products of this geometric universe, are so perfectly tuned to comprehend its mathematical harmonies. So the next time you look up at the night sky or marvel at the symmetry of a snowflake, remember that you are not just seeing light or ice. You are glimpsing the timeless geometric order that underlies all of reality, a continuous cosmic conversation between the universe and the curious minds that seek to understand it. Thank you for joining us on this extraordinary